We are into chapter 5, sensitivity analysis. So we had a taste last time already where for a small system we could completely characterize the sensitivity analysis, right? And let me put that problem up because now we're going to change some other parameters and see how we can analyze. Okay, so let's see. I have, from last time, the problem from last time. We're going to do that. So we have the minimize 14x1 plus, no, 14x2. That's z. Subject to 10x1 plus x2. Okay, so that was the problem from last time. It has two variables and two constraints that you can draw. You can sketch the feasible region and you can sketch the contour lines for the objective function, and you can visually see which point will be selected as the optimal point, right? And then based on that, we did a sensitivity analysis that is changing these two numbers, call it C1 and C2, how does the solution respond to it? Remember, by drawing the graph. Okay, so today we're going to pick up something else. So let's say the farmer started to doubt about the nutrition value that's being set. Or he wants to see that if I feed my chickens, whatever, a higher nutrition value than the requirement, will it make them grow faster and maybe I get more money? Is that right? So he wants to see that. Okay, so let's see. Now I want to change these two. Let's say the nutrition value for element A and B now is set to be required to be bigger than B1 and B2. And I want to see how the solution changes responding to that. Is that clear? So it's another dependence. So we still want to do it in the setting of a graphing method. Then if you want to do the graphing method, so we make this observation. Let's say I want to do the graphing method for this. What will I have to do? I will have to draw this line with the parameter on the right-hand side that I should be able to move. And then I will end up moving this line up and down. Is that right? And I'll have to do the same thing for the second constraint. So my feasible region will have to be changed. And it's very hard for me to see how the optimal solution will respond to that. Do you agree? And graphing it is also annoying. So I would just say, okay, it's a bit difficult or annoying. I would like to still stick to the graphing method that we did last time. Like the feasible region is fixed. I just need to check the slope of the contour line. That's much easier to analyze. Do you agree? So how can we change this problem into that setting? What we have learned, what have we learned? Some other problem that give you the same solution as this one. That is the dual, right? Okay, so let's consider the dual and see what happens. Okay, so the dual would be maximize. So I have y1, y2, right? V equals b1, y1, b2, y2, subject to 10 y1 plus 3 y2 less than 16 4 y1 plus 5 y2 less than 14. Okay, so now this is more or less in the same setting as the problem we looked at last time. That is, the feasible region now is fixed, it's not changing, and I'm changing my objective function, right? And the change in B1 and B2 will cause a change in the slope of these, the objective function. Then you can move it up and down and locate the optimal point. So let's do this like briefly. So I think we should be pretty comfortable with this setting. So let me sketch. So this is y1 and this is y2. I'm considering only the first quadrant. So I will draw the line with the equal sign and the line with the equal sign and take the region below the line. Is that right? Because I have less than equal. Okay. So if I do that, I will have the following. So let's say this one here is the line L1. So L1, let's say this one corresponds to the line L1, and this one gives me line L2, and this gives me L3, like our notation from last time. Let's still do it. So this is L1, and then I have an L2. Okay, not draw to proportion. So this is coming from the second constraint, okay? And then it's below, so my feasible region will be this quadrilateral. Is that right? So I have 4 vertices, and I know this is not a candidate, and let's label the other 3, P1, P2, and P3, and you can find their numbers, 0, 14 over 5, P2 is 1, 2, and P3 is 8 over 5, 0. I know these. Okay. Okay. And then I draw the contour line of this V, and depending on the value of B, it will take certain slope. So L3, what do I know is the slope of this would equal negative B1 over B2, right? Depending on the slope, as I come down, I'm trying to maximize, yeah. So as I come down, it becomes smaller and smaller. When it touches the feasible region for the first time, that will be the maximum value, because if I move further, it becomes even smaller, right? So depending on that slope, I might hit this point, or I hit this point, or I hit that point first. Is that clear? It's more or less the same as last time. So let's get these slopes. So I have these slopes. S1 will be negative 10 over 3, and S2 will be negative 4 over 5. Okay? And we can do a similar discussion. So we have the following discussion depending on the slope. If I know the S2 is less than S3. So let's say the slope is very big, meaning flat, not steep, right? Steep down will be smaller. And then is more flat, and I will hit P1. Agree? Okay. So you would get P1 as your optimal point. And then if it's between S2 and S1, and then that will be as illustrated here. As you come down, you will hit P2. Okay? And the last one is if it's very, very steep, and then you will hit P3. So if S3 is even more steep than S1, more steep than this one, then you will hit P3 as the optimal point. Is that clear? Okay, now I can state, going back, state it as B1 over B2. So you can conclude the maximum value of the dual can be determined as the following. So if I hit P1, what will be the value? So at P1, I have y1, 0, y2, 14 over 5. So I get B2 times 14 over 5. Is that clear? So it will be 14 over 5 B2 if, so let's state this slope. So that means the ratio here actually is less than that ratio. So it's less steep, so it's bigger. Okay? Okay, and then if I hit P2, then I will have 1 times y1 plus 2 times y2, right? So y1 plus 2 y2 if 5 over 4 less than b1 over b2 less than the other slope, that's 10 over 3. Is that clear? Okay, and then the last one, you will hit P3, then the, oh, no, I'm sorry, this is B1, B2. Why did I write Y? B1 and B2, because, yeah, so the other's the Y value. So Y1 is 8 over 5, so I will have 8 over 5 B1, and Y2 is 0. Nothing comes from there. And that's if B1, B2 is bigger than 10 over 3, that it's very steep. Okay, so this analysis is done on the dual. Then you have to go back to the original problem, isn't it? This maximum value is the maximum value for the dual, and then you can say simply, quote, duality theorem. And that's all. This max equals the mean of the original problem. Okay, and then you have a complete analysis of this sensitivity with respect to change of those parameters. Is that okay? So this is in a very particular situation that you have full information using graphing method. But the graphing method is very limited, isn't it? You cannot have more than 2 variables. If it's 3 variables, I cannot draw in the 3D. It's very hard to see, all right? So let's take a little sneak peek there. We'll just take an example. We're not really giving any theorem, so I think that's the next example in the textbook. So, okay. Yeah, okay, let's represent this as a word problem again. So it's a production problem. You want to produce 2 products. So let's quickly set this up. So production problem, I need to produce 2 products, A and B. And then I have resources. So let's say aluminum. I could say resource 1 and 2. Let's be aluminum and machine time, how much I can use, and let's say that's labor. Okay? And then to make each boat, I need to do things. So I have data here, and then for the resource, I have limit. I don't have infinite amount of resource, right? And then for each product, I have a price. So I'm trying to maximizing my profit within the limited resource. Is that clear? That's the setting. So I'm going to fill in, these are just numbers. Let's fill in the numbers. 50, 30, 6, 5, 3, 1, 2000s, just number, 300. Okay, so that's the data we're given. And for each boat, I have a price tag, and provided I can sell all of them. All right, so Are we okay setting up the model for it? Let's set up the model. So my x1 and x2 would be the amount of both a product A and B that I'm going to make. Okay? So okay, x1, x2, number of product A and B, respectively. So I can set up my maximization. So maximize, what is my profit function? That will be 50 x1 plus 60 x2. My constraint, subject to. I have 3 constraints, right? One from each resource. So I'll have 50 x1 plus 30 x2 must be bounded by the limit. It cannot be more than that. And 6x1 plus 5x2 bounded. And the third one, 3x1 plus 5x2 bounded by that. And of course, non-negative. Are we okay setting this up? It's very standard, right? We can just write it out, right? It more or less follows the form of this table, actually, isn't it? You copy down these coefficients, you copy down the right-hand side in a correct way, and that's all, okay? So now the question now would be, okay, so if I put this into, you can solve this quickly in LP Assistant. Let's try to do that. I actually launched this up. So let's see. If it allows me to do it quickly. Screen. Going down. Come on. You need to find me. Is it up? Oh no, why you do this to me? What happened to my LP Assistant? Okay, let me try to open it. Okay, I actually had it all prepared, but now he quit, so I have to punch in these numbers. It won't take long, just 1 minute or 2. So let's put in the number. So we see the constraints are less than equal sign, and you see if you add slack variable, they'll be conveniently serving as your basic variables, right? So I have 50, 30. I add a slack for the first. I have 2,000. And then for the second one, I have 30. No, not 30. It's 6, 5. And that's the slack. And 300. And the last one, I have 3, 5, 1, 200, right? And basic variable, x3. These are the slack variables, x4 and x5. And I need to put in a minimization problem, so I get negative 50 and negative 60. Is that right? Did I punch all the numbers correctly? Okay, let me remove the light. Yeah, okay. So let's pivot. Okay, so let's choose this one because it's big and negative. Ratio 40, 60, 66. So I click on 40. Let me move it down. And I still have a negative. Let's check ratio 66, 33, 25. Let's click on that. Okay, now it's done. 2 steps. Do we see? Are we okay? So let's leave this over. So I see that that's the optimal value. And it's attained at x1 is 25, x2 is 25. And x3, no x3. And then I have actually some slack variable from x4, which is the second constraint, right? Okay, so let me put, I'll leave that there, and let me turn on the light. Okay, let's write down what do we have. We found out I have the solution as the following. The z max, I take negative of negative, I get that number 2750 attained at x star. The optimal was 25, 25. Okay, so we solved that problem. And now, something changed in the situation. Let's say the supply for one of the resources, let's say this number here, the supply for the aluminum, the first equation, is now different. I might get more, or maybe there's a shortage, I'll have less of that. So my question will be, how does the change in that number, 2000, affect the final solution? Is that clear what I want to do? So my question now is, how does the change in this number, how does it alter the solution? Okay, so this is changing something in the constraint. I will be changing the constraint. It's not so nice to see. So let's write out the dual and try to get some help from the dual. So for the dual, I'll be putting up 3 variables, one for each constraint. Is that right? I have to do the minimizing 2000 times y1, 300 y2, 200 y3. Let's call this v, and I have the constraint subject to whatever. So, okay, so the constraint is unchanged. So let me copy. I really don't need to do this. So that is the dual. So let me block the parameter that is going to change. So this number will change, and I would like to see how it affects the solution. And then you see that in the dual problem, this is clearer, isn't it? Because once you find the minimum of the v, you know it will equal to the maximum of the z by duality theorem, right? So here, this number is in the expression of your objective function. So you see clearly how I change this number will affect the final v value. It's clearer. Do we agree? Okay. So do we know the solution for this dual problem? Isn't it here in the tableau? The y, the optimal y value will be here. Is that right? Okay, so we actually immediately have the following, that is v min would equal the same if I solve it with this 2000 there, okay? And at the optimal value, let's copy down 7, 16, 0, and 75 over 8. And let's call this y star. Okay. Now I can do the following analysis. Okay, so I apply duality theorem. So the duality theorem says the maximum of the z equals the minimum of the v. Is that right? So how did I compute the minimum of this v? Well, you know, it's obtained at this optimal point, so it's this coefficients there, and I plug in the y value. Is that right? So let me write this out so you see more clearly what that is. So I have 2,000 multiplied by 7/16 plus 300 multiply 0 plus 200 multiply 75/8. Okay, so let's block the one that we are making change. This one, we're not so sure. The value might change. Now, is it clear from this expression how the Zmax will change if I change this 2,000? If I change the 2,000, if I increase 2,000 by 1 unit, how would that change in the Zmax? Well, it will change by a difference of 7/16. Is that right? Is it clear? So let's, but there's something else. Okay, let me write down. Conclusion. Okay, so we have to be careful. This expression is valid as long as the y star here is the optimal solution. If the optimal solution shall change, you know, if you change this 2,000 into big number changes, you might change the optimal solution. Then this expression is not valid anymore. Okay, so I will have to write as long as the y star remains the optimal solution point for the dual, okay, I can conclude the following. So, an increase in an increase, let's say, oh, so it's very silly, this wording, of a unit size in this number 2,000, this number here, if I make a little change there, will cause a increase of 7/16, that much amount in the Z max. I can conclude that, okay? So I want to emphasize that this is really important, that y star remains optimal. We don't really know if I make a change, it will change or not. Okay, so we will talk about this in more detailed analysis. Okay, and then you can say the same thing about changing the other. Let's say I want to change the total number of labor is different. Maybe I hired more people, maybe someone quit because I'm a bad boss. So that number is changed, and what happens, right? And then you see that if I change this number, as long as y star is unchanged, and the change in here will cause this much in the profit. Is that right? So in a way, you can say that these three numbers, there's some kind of a price tag, isn't it? If you change 1 unit of this, that's what it's going to cost you. Do you agree? In your profit. If you change 1 unit of your labor, and that's how much it's going to cost you, right? So here, that's why they have a name. This is called shadow price. Okay, the price that's kind of hidden in the model. If you change the constraint, actually it affects. So the shadow price will actually be exactly the solution of the dual. That's why the dual is so important. Give you the shadow price. Is that clear? So what does it mean by this is a price? Okay, 1 unit change causes 1 unit change in the profit. Okay. Another thing that's interesting here is this 0. So you see, if I change this number here, so the price for that is 0, meaning if I change this, as long as y star still remains as my optimal solution, it has no effect to the Z max. Why is that? Can you see it? pinpoint what is causing it. So I make this curious observation. Price, let's say, price for the shadow price for machine time. Let me call this shadow price. In this part is 0, and I'm curious, why? So the machine time, the constraint is in the second equation. Is that right? Has to be less than 300. And the slack variable we add on is x3, x4, x5. So x4 is the slack variable for this equation. At the optimal solution, we see that x4 has a positive value, while x3, x5, they are 0. Meaning, at the optimal solution, this is equal, and this is equal, and this is strictly less. Is that right? So let's make that connection. So we see the slack at x star, the optimal solution is the following. So I have 0, and then for the second one, I have 25 and 0. So this one is strictly bigger than 0. That means this machine time is an underused resource. It's not being used to the requirement. So if you change the requirement, I change this 300, let's say I have 400 hours of machine for me. It doesn't matter because I'm going to use only 250 anyway, so it won't change my price. Does that make sense? Okay, so just making these connections here. Okay, so let me write. So the machine time here now is an underused resource. Okay, so if you make a little change, not too much, not until y prime becomes not the optimal solution, then it has no effect to the final optimal value. Okay. Okay. So, is that clear? How to use the dual? The solution of the dual give you the shadow price. Maybe I should highlight. So this is actually the solution, optimal solution. Solution of the dual. Okay, that gives you the shadow price. So that's why it's important, the dual problem. Okay, in many settings, that's one thing. Is it okay? Any questions? Now I would like to go back to this thing that I blocked here. As long as y star remains the optimal solution, but we don't know, right? If I make a change, if it's too big, it might not be. So I don't know. And from the LP assistant, there's nowhere you can see. It just gives you the solution and the solution of the dual you can read from the tableau, but nothing beyond that, right? From what we know so far. So, so for this question here, and actually the answer would be in the, if you use Excel, and it gives you something called sensitivity report. Okay, so I just want to take a look at that sensitivity report just to point out what is in there, and later on we'll talk about how one get those things. Where's my Excel? Okay, so sheet, is it sheet number 4? No, sheet 3. Sheet 1, where is it? No, I lost that sheet. I prepared all these and I'm not finding it. Okay, there is that sheet that I made. So we all know how to use Excel. So I punched in my model in the Excel with a constraint, with variables, and then set this up, and I clicked solver, and I solved it, and they give me this number, 2750. Are we all okay with doing that? I don't want to punch it in front of you. It takes a couple minutes. Okay? So after you have done that, let's hit solver again. Now, let me show you where you can find this sensitivity report. So after you have done solver, and you say solve it, and it pops up a window. Here you see there is a thing called sensitivity. You can click on that, and you can click OK, and then you will have a sensitivity report shown up here to you. Okay, so let's take a look at this sensitivity report and see what is in it and how we can read from this sensitivity report. So first row here, final value, that will be the optimal solution for the x, x1, x2, which is 25, 25. Is that clear? And these are the final value of your constraints. So at that point, you got 2,000, 275, and 200. And then you see these have 0 slack, and this one has a 25 amount as slack. Is that clear? Okay. And then it also lists the shadow price. Okay. There it lies the solution to the dual problem. Now you know shadow price is the solution to the dual problem. If you set up the dual, this will be the optimal solution point for the dual problem. Is that okay? That's how you read that. Okay, and there are these coefficients. And then these two are maybe of interest. So here it says allowable increase, allowable decrease of these resources. So what it says is that if I take this 2,000 here, and I keep all the other coefficients unchanged, and I make change alone in that number, how much can I increase it, and how much can I decrease it, so that these optimal solutions are not changed? Is that clear? That is this question, as long as y star remains optimal. So how much I can change so that statement holds. Is that clear? So here it tells you how much you can increase to that value, then the y star, x star. They're not changed. And then how much you can decrease. And if you decrease more than 800 units out of that, then the x star will be different. And then this doesn't work anymore. Is that clear? And that is the same for the machine boat. You can increase as much as you want, but you can decrease 25, and you see that is exactly the slack amount, right? If you make the constraint 300, reduce more than 25, then you have something less than 275, and then this doesn't hold anymore, and you have to change the optimal solution, okay? And then that will be the change allowed for the labor, okay? And then it also gives you analysis of what you can change here. That will be the price for the both A and B. If you change a little bit the price, and how much the y star will not be changed. Okay, how much you can increase, how much you can decrease, so the optimal solution point is not changed. Is that okay? That's what I want to show you. But how do you get this bound? Well, we'll get into that. All right. Any questions so far? We're okay? All right. So I think that's all I want to show in Excel. How much time do I have? Okay. So I have half an hour. Let's enter the next. So we're going to do some analysis. We're going to figure out how to understand all these sensitivities. Okay. So I will go into. If you want to talk about it in a more abstract setting, and with compact notation, we will use matrix notation. Okay, and for the simplex algorithm. Okay, so I will show you what how we do that. So okay, let's set it up. So consider. So we are rewriting the simplex algorithm by, instead of putting all numbers in, I'll put a matrix in. You basically take that coefficient block and call it the matrix. Is that clear? That's all that is, okay? So, and we have a problem in standard form and in canonical form, right? So we have a problem in standard form, and it has to be actually in canonical form. Okay, so minimize Z plus Z naught equal Cx subject to Ax equal B, x bigger than 0. Now here I'm going to use a little bit different notation here. Here, because when you put in the tableau, the coefficient C takes a horizontal shape. So I'm going to define a row vector for C. Is that okay? So it's a horizontal one. So here, C is a row vector. Okay, if it's a column vector, then you have to write C dot x, right? Okay. So here C is a row vector, and x is a column, and so you know a row vector multiplied by a column vector in the end is a number. Okay? Okay, so I can denote the initial tableau as the following. So you in your simplex tableau, you know, what you put here is the A matrix, and what you put here is the B vector, the right-hand side, and what you put down here is the C. Now it's a row vector, so it lies flat, okay? And then what you put here is the 0. So I will write like that. Is that okay? That will be the tableau. And then on the left, it will be indicated which one is the basic variable, but I'm not writing it there. Is that okay? And then you know, what does the simplex algorithm do? It performs some pivoting steps and blah, blah. We're all familiar with that. And then in the end, let's say the optimal value is found. And then you have the final tableau. Is that right? So I'm going to denote so after pivoting steps, okay, I will have the final tableau. Okay. I'm going to denote it by just putting star on everything. Then this A matrix will be changed. I call it A star. And the B vector is changed, B star. And C is changed. I call it C star. And Z naught is changed. I call it Z naught star. Is that okay? The starred ones are the final ones. Is that okay? Okay. So you know the final form has to be in canonical form. Is that right? So what do we know about the final form? So let me put it here. So this final form, let's call the final form F. This is the initial form, initial problem, initial 1i. So we know that f is in canonical form. Okay, so with a set of basic variables. Right, and your basic variables actually will be listed on the left here if you use LP Assistant. It keeps track of which one remains basic. Is that right? You actually know. So you will have these x5, x1, whatever, as you have seen in the LP Assistant. You have a bunch of listed basic variables. So I need to know who they are. Okay, so I would trace the index of these basic variables. And okay, so in the general setting, what will I have? Okay, so let me say here. This will be listed on the left. Okay, on the left, if you use the LP Assistant. Okay, just to tell you, you can get that information easily. Okay. Okay, so I will denote these by, in particular, I will denote the indices of these basic variable as J1 is the index for the first one, and J2 is the index for the second, and I shall have m of them. Is that right? I have m of these. Okay. I have to set up this. Okay. All right. Now let me. So you know on the tableau here is listed x1, x2, all the way to xm. You have all these x listed. And then I will take out the corresponding columns in the A matrix, and I will denote it. So let's introduce this notation. I need to take out columns of A. So if I have a matrix A, and then I put the index J on the top in the bracket, what do I mean? That will be, I'll take a column vector, I take the Jth column. Is that clear? I just take that. So this will be the Jth column of the A matrix. Is that okay? Okay. Now I'm going to take out all these columns because now I see I have m indices. That's the basic variable. In this order, be careful, this order must be the same as they are ordered here, the top one to the last one. Okay? You can't randomly pick it. It has to be following that order. Okay. Now I'm going to take out all these columns. Take out these columns in A. So this A, any of this J, J1 dot to A, Jm, I'll take them out. So I will have m of these columns, right? And each one is of size m. And I just form a square matrix. Is that okay? So I form a m by m matrix. Okay, and let's call it B. This matrix will be fussing over and over. So that's taking the A. Be careful, that's the A from the initial tableau. Okay? No star on it. Okay, so the J1th column and A J2th column and until the A Jmth column. So you know this is a square matrix in the end. Okay? I'm going to set up all these notation. Okay, and I need a few more things. Okay, should I go all the way over here, so far away? Okay, let's do that. Okay. So I will also take out the same position of the C coefficients. Is that okay? I'll take the 1 times m, this will be a row vector, from the C. So C, I call this vector CB. What do I take from is these C coefficients. That's the original one at position J1. Okay, I can call, so this is okay, C J2 to C J. Okay, I'll give you an example too, so you have a concrete idea where they are. Okay, so I have the claim, which will prove, maybe not today. I claim the following. Once the A matrix, the initial tableau is given, once you know at the end who shall be the basic variable in the final tableau, then all these A star, B star, C star, Z star are actually determined by the initial tableau in the following way. So I will write out, we claim a few things. So A star simply equals B inverse times A, okay? And B star equals B inverse times B, okay? And C star equals C minus CB, B inverse A. So the B, you know, we defined it. The CB, we just defined it, okay? Okay, so, and here we observe B inverse times A is just A star, so this is also C minus CB A star, right? The same thing, okay? And the final value Z star would be Z0 minus CB, B inverse of B. And actually, B inverse of B you know, because it's computed over here. So I can write it as Z0 minus C, B, B star. Okay. The proof will come a bit later, maybe next class. Oh, I just got a paper cut. It's annoying. Okay, so I will give you an example, so you will see how do you extract the B matrix and the vector CB and how all these things play out, okay? With some numbers, so a concrete number. So let's take an example before we jump into the proof. So what do we mean by that? And in this example, we actually will verify the claim for this example, okay? And then we'll have a general proof later. Okay, so let's see. I want to minimize the thing. Z is 5x1 plus 3x4, 2x5 plus 21. Just numbers subject to -6. Oh, I don't have to write it so over. Let me start from here. I have two constraints, -6, x1 plus x3 minus 2, x4, 2, x5. This is in canonical form. Okay. Okay. So you know the original, this problem is already in canonical form, and you can put it in the LP assistant. If you want, you can do that. You will have the following. So I'll put these on the blackboard, because then I need to go and point at these numbers. They are what I'll show you where I take out all these information. All right. So let's take the initial tableau. Here, I'll put everything in. So you see that x3 is the basic variable, and x2 also for the initial tableau. Okay, so I have 6, 15. Let me put the number -6, 0, 1, -2, and 2, -3, 1, 0, 6, and 3. And the z is 5, 3, -2. Oh, no, that's wrong. 5 and 0 here, 0 here. x4 is 3, x5 is -2. And z0 is -21, because you have to move this to the left-hand side. Okay, so this will be the initial tableau. Okay, that's the initial one. And then you could easily set up in LP Assistant. You did pivot and a couple steps, and then after some steps, you get the following. And now you have x5 and x1 over here. And let me copy these numbers. So I have 0, 1. I have not so nice number, 1, 6, -1, 4, -1, 4, 7 over 2, 3 over 2, 1, 0, 6, 1. That's the A star part. And I have 0, 1, 6, 3, 4, 5 seconds, 0, and -14. And you see, if you have reached a state like this, and you look at the coefficients, the C's, they're all non-negative, so you're done. Is that right? So this gives me the final tableau. Okay, so now I'm going to show you how to find the B matrix and all that, and then we'll verify our claim on this example. I probably need more space. So is it clear where's the A, where's the B, where's the C, where's the Z? This is the A matrix, right? It has 5 columns and 2 rows. And that's the B vector, and this will be the C, and that's the Z0, right? And the same thing here, then this will be the A star, this will be the B star, that will be the C star, and that's the Z0 star, okay? And we want to show that this relation for equality holds for this example, all right? Okay, so I need to form the matrix B. How do I form the B? B, it says you should take the A matrix of, the first one is column 5, because that's 5. Is that clear? A column number 5, and then you take the A matrix, column number 1. Okay, from the A matrix, not from A star. So column 5 will give me 2, 3, and column 1 gives me -6 and 3. So I have a square matrix. Is that okay? So be careful, the order matters. the fifth column comes first, and then the first one. It follows the order of the basic variables. Is okay? All right. And then I also see that I need B inverse. Are we okay making inverse matrix of 2 by 2? There's a quick formula. You compute the determinant, which here is 12. So 1 over 12. And then what do? I lost the negative sign, sorry. Yeah. And then you flip the diagonal ones, -3, 2, and then you change the sign. No, and then you keep, and then you keep change the sign, -3 and 6, right? You can form that inverse. You can verify that it is an inverse. Okay, and then I also need to find this vector C of B, which is taking the same position, but in the C coefficient. So I will first take C5, which is -2. And then I take C1, which is 5. Is that clear where you get them? Right? So we have to follow the order of the basic variables. Right? Okay, now let's verify. It's just a computation, isn't it? So let's compute B inverse times A. What will I get? Well, B inverse is given 1 over 12 and -3, 6, -3, 2, and multiply by the A matrix, which is just there. So negative, let me copy this. 6, 0, 1, -2, and 2, -3, 1, 0, 6, 3. You can easily do this product, right? You could probably open some software, MATLAB or whatever. You can easily verify this product, and you'll be convinced that you just get the A star. So, okay, let me just be silly and copy this number down. 1, -½ 1/4, 7, 2, 1, 1, 1/6, -1/4, 3 over 2, 0. So we verify the first, okay, for this example. And then we can check the second one. So what is B inverse times B? So 1/12, -3, -3, 6, 2. And where do I find the B? Well, it's the right-hand side, right? 6, 15. Well, this is just, you do the inner product of this with that and divide it by 12, and inner product of this with that and divide it by 12. You can easily verify. I will get 6, 1, which is just B star. Is that okay? Now let's verify the third one. So let's compute C minus B, CB, A star. So what is the C? Well, C is this long vector. So let's copy it down. 5, 0, 0, 3, -2. That's my C minus CB. I have it, -2 and 5. And then I need to multiply this with this A star, which is here. That's my A star. If you do, so you see this is a row vector of 2 entrants. So you will have that one, dot product this vector, that's the first element, and dot this vector, the second, so on and so forth. Okay? So if you carry this out, I get the following: 5, 0, 0, 3, -2, minus, if you want to verify that, you're welcome to work out the details. 6, -3, 4. I have -2. Then you get this vector, which is a row vector. And then you do subtraction. And that's a 0, sorry. This minus that, each element subtract with each other. Okay? So this gives me, sorry, I'm writing it really long. So I got 0, 1, 6, 3/4, 5/2, and 0. So that is exactly this vector we have here, the row vector. Okay, and that's my C star. Is that okay? And okay, you can verify the last one by yourself if you want. So Z0 minus CB times B star, the last one, I want to verify that it actually gets me to this, the final value there. So I get -21 minus, what is my CB? I have it here, -2 and 5 times B star, which I computed here, and 6 and 1. Okay, so I get -21 minus, and if you do this inner product, what you get? -12 and a 5, that gives you -7. Is that right? So you add all these up, you get -14, which is the number down there, Z0 star. So is it clear what this statement means, that these relations should hold? We just verified it for one case, right? And we haven't proved that. So next time, we'll go about and prove this. Okay? So next Tuesday, I'm thinking probably we use the first half an hour, just go through that proof, and then we'll do a review. And I will post the study guide online. You try to review during the weekend, try to have some concrete questions to ask. And then I'll put additional office hours as well. Is okay?